We've already seen, both in chapter 1 and in the property 3 that we just discussed, that optimal solutions of a linear programming problem seem to always occur at corners of the polyhedron, describing the feasible region of the problem. What we want to do now is give a mathematical definition of a corner point. In fact, we're going to give 3 possible definitions of corner points. So all definitions that seem reasonable to us in order to describe a corner point, and then we're going to see how they're all equivalent. If you're wondering why we need to introduce 3 different definitions of corner points, it's because later on it will be very useful to use all these 3 definitions to prove several different properties of our linear programming problems. To differentiate these 3 different definitions, we're going to use different names for the 3 of them. The first is the definition of an extreme point. So what's the idea behind this definition? This pentagon down here will be our running example. Here, the points that we want to define, so those points that for us are informally called corner points, are clearly 5. This one down here, this one, this one, this one, and this one. So how can we come up with a mathematical definition? Here's the idea. So for any point that is not a corner point, we can always find 2 other points in the polyhedron such that our point lies in the segment connecting them, like this guy W over here. However, you can never do that for a corner point. For example, look at this vector x over here. No matter how hard you try to find 2 vectors, let's say y and z, for which x lies in the segment joining y and z, at least one of them must be outside the polyhedron. So this gives us then the idea behind this definition. Let's see the formal statement. Let P be a polyhedron. A vector x in P is called an extreme point of P if we cannot find 2 vectors y and z both in the polyhedron and different from x, and a scalar lambda such that x is equal to lambda y plus 1 minus lambda z. In order to understand that this definition in fact matches our original idea, everything you need to do is to check that the points that can be written as lambda y plus 1 minus lambda z for lambda in the closed segment 0, 1 are exactly all those points in the segment joining y to z. Before moving on to the next definition, I want to point out that this definition is entirely geometric. So what does this mean? Definitions over polyhedra are said to be geometric whenever they depend on the polyhedron, but not on the specific algebraic representation of P. Namely, if there are 2 different systems of linear inequalities defining the same polyhedron P, then the set of extreme points are exactly the same, because as you can see in the definition, we always refer to P and never to the actual system of linear inequalities defining it. And this discussion immediately brings us to an interesting question. Is it really possible that 2 different systems of linear inequalities give rise to the same exact polyhedron? And the answer is of course yes. For example, think about this polyhedron P over here. Now this polyhedron could be defined by 5 linear inequalities. The one corresponding to this line, the one corresponding to this line, to this line, this line, and this line. These are 5 linear inequalities. However, you can add to this system, for example, another inequality. Let's say you take the half space on the left of this vertical line that I'm drawing. Then the polyhedron P doesn't change at all, but it's defined with one more inequality. And you can see that in this way you can add any number of inequalities that don't change at all your polyhedron P. So now that we've understood what it means for a definition to be geometric, I want to point out that geometric definitions are extremely helpful, especially in order to understand the geometry behind the problem and to give us an intuition of what's going on. And they're often very simple to understand. However, geometric definitions are often difficult to work with from an algebraic perspective. Let's now look at the next definition that we proposed for corner points. And in this definition, my corner points will be called vertices. What is the idea here? We've already discussed how corner points have a nice connection with optimal solutions of linear programming problems. And in fact, this definition goes exactly into this direction. The idea here is the following. This vector x, which is for us a corner point, is the unique optimal solution of the linear programming problem with feasible region P and where we minimize C transpose x, where C is this vector over here. And not only x is an optimal solution, but it's the unique optimal solution. This means that there's no other optimal solution to this linear programming problem. On the other hand, for this vector w over here, which is not a corner point, it might still happen that it's an optimal solution to a linear programming problem with feasible region P. For example, it is an optimal solution if C is given by this vector. However, it never is the unique optimal solution. For example, in this case, all the vectors on this line segment are also optimal solutions. This allows us to write down the definition of a vertex. We have a polyhedron P given. A vector x in P is a vertex of P if there exists some C such that C transpose x is strictly smaller than C transpose y for all y satisfying y in P and y different from x. This is equivalent to saying that x is the unique optimal solution to some linear programming problem with feasible set P. Note that also this definition is entirely geometric. In fact, we never care, in this definition, about how P is given to us. We only check if vectors are in P or not. So also this definition gives us a very intuitive view of corner points, or better, of vertices. However, at this point, we have enough geometric definitions to fully understand the concept of corner point. What we want to have next is what is called an algebraic definition, which is a definition that uses explicitly the given system of linear inequalities defining P. Having such a definition will give us a big advantage, because then checking if a vector is a corner point or not will just be possible with a simple algebraic test. The third and final definition of corner points that we're gonna see requires first a number of technical definitions. The first definition is of a constraint being that of a constraint being active at a vector. To give this definition, let's say we have a polyhedron in Rn defined with a bunch of linear constraints of the form greater than or equal to, less than or equal to, and equal to. The corresponding indices of the inequalities are m1, m2, and m3, all finite index sets. So let's get now to our definition. If a vector x star satisfies AI transpose x star equal to bi for any I in one of those three index sets, then we say that the constraint I is active at x star. So essentially, a constraint is active at x star whenever x star satisfies the constraint but at equality. In the case of M3, it really just means that it satisfies the constraint, because also the original constraint was an equality constraint. However, in the case of M1 and M2, then it means that it doesn't just satisfy the inequality, but it satisfies it with the equality sign. Let's see an example here. We've already seen the polyhedron in the example, which is defined by non-negativity inequalities x1, x2, and x3 greater than or equal to 0, and the equality constraint x1 plus x2 plus x3 equal to 1. In the picture, we have a number of vectors that are highlighted. These are A, B, C, D, and E. So we can check for each of them which are the active constraints among those that define P. A is the vector 0, 0, 1. Therefore, the active constraints are x1 greater than or equal to 0, x2 greater than or equal to 0, and x1 plus x2 plus x3 equal to 1, because all these three are satisfied at equality. x3 greater than or equal to 0 is not active at A, because while it is satisfied, because the component 3 of A is equal to 1, and 1 is greater than or equal to 0, 1 is strictly larger than 0. So such a constraint is not active at A. The vector B is the vector 1, 0, 0, while the vector C is the vector 0, 1, 0. And I leave it to you to check which are the active constraints at these two vectors because it really is symmetric to A. So let's instead look at the vector D. D is the origin. So the constraints that are active at D are x1 greater than or equal to 0, x2 greater than or equal to 0, and x3 greater than or equal to 0. On the other hand, the equality constraint x1 plus x2 plus x3 equal to 1 is not active at D, because the sum here is 0, which is different from 1. Finally, let's look at the vector E. From the picture, it's clear that the vector E has component x2 equal to 0 and both x3 and x1 strictly positive. Therefore, the constraint x2 greater than or equal to 0 is active at E, while x1 greater than or equal to 0 and x3 greater than or equal to 0 are not active at E. Furthermore, x1 plus x2 plus x3 equal to 1 is active at E because you can see in the picture that E lies in the triangle representing P. Great, we're almost ready to give the third definition of corner point. And such a third definition is that of a basic feasible solution. But to get there, first we define what is a basic solution. So let's read through the definition. Consider a polyhedron P defined by linear equality and inequality constraints, and let x star be a vector in Rn. Then x star is said to be a basic solution if both these conditions apply. The first condition says that all the equality constraints are active, which simply means that all the equality constraints are satisfied. Secondly, out of the constraints that are active at x star, there are n of them that are linearly independent. And note that n is the maximum number of constraints that can be active at x star and linearly independent, because our space has dimension n. Recall that the number of constraints with left-hand side AI transpose x are said to be linearly independent if and only if the corresponding vectors AI are linearly independent. So essentially we only look at the left-hand side of the inequality and not at the constant in the right-hand side. We're finally ready to define a basic feasible solution. A basic feasible solution is a vector x star that is a basic solution and it also satisfies all the constraints. Let's now get back to our latest example and discuss which vectors are basic solutions and which are basic feasible solutions. The first condition in the definition of basic solution is that all equality constraints are active. Now there's only one equality constraint here, which is x1 plus x2 plus x3 equal to 1, and we can immediately see that the vector D is the only one that doesn't satisfy it. Therefore, D is not a basic solution, and therefore it's not a basic feasible solution. So now we can focus on the remaining ones. All the remaining vectors A, B, C, and E satisfy condition 1. So now let's check the second condition. So for each vector, we need to look at the active constraints at the vector and see how many of them are linearly independent. Let's start with A. Once again, the active constraints for A are x1 greater than or equal to 0, x2 greater than or equal to 0, and the equality constraint x1 plus x2 plus x3 equal to 1. These are three active constraints, and it's simple to see that they're all linearly independent. Therefore, this is a basic solution. To check if A is also a basic feasible solution, we only have to check if it satisfies all the constraints, which means if it is in P or not. Of course it is in P, therefore A is a basic feasible solution. Symmetrically, you can also check that B and C are basic feasible solutions. So now let's look at E. The active constraints at E were x2 greater than or equal to 0 and x1 plus x2 plus x3 equal to 1. These are just two constraints that are active at E, so there can't be three of them that are linearly independent. Therefore, E is neither a basic solution nor a basic feasible solution. Let's see now another example, and this time we're going to look at dimension 2, so n is equal to 2. In this case, I only give you a picture of P. and I assume that the system of inequalities that gives me P is the one that has exactly one inequality per line that appears in this picture. So we have a total number of 4 inequalities in the description of P. In this case, there is no equality constraint. If there was even just one equality constraint, then our feasible region P would be contained in a line, and this is not the case. Therefore, there is no equality constraints defining P. Therefore, condition 1 is automatically satisfied, and we only need to check condition 2 in order to understand which are the basic solutions. It turns out that all these vectors A, B, C, D, E, and F are basic solutions. Why is that the case? The first thing to understand is that a constraint is active at a vector in dimension 2 if and only if the vector lies on the corresponding line. Furthermore, in dimension 2, two inequalities are linearly independent if and only if they're not parallel. Therefore, regarding A, both the constraints corresponding to the line passing through A are active at A and they are linearly independent because they cross. Great, but which now are the basic feasible solutions? Once again, this is easy now that we know all the basic solutions because we only need to select those that are also in the polyhedron P. Therefore, these are C, D, E, and F. So we're excluding A and B, which are basic solutions, but they are not basic feasible solutions. One interesting observation is that if you are considering a polyhedron in Rn, which is defined by m constraints, and m is strictly smaller than n, then there can be no basic or basic feasible solution. Because for sure, the number of active constraints at any given point is smaller than the total number of constraints, which is then strictly smaller than n. So let's recap for a minute. What have we done so far in this video? We have thought about the concept of a corner point, and we have given 3 different definitions that are supposed to capture such a concept of a corner point. 2 of them were geometric, extreme point and vertex, and in these 2 cases we understood the definition very clearly from a geometric point of view, and the third is algebraic. And in fact, the definition is much more technical, less easy to understand where it comes from. However, it gives us a very useful tool to check if a point satisfies this algebraic condition, as we saw in the examples. What I want to show you next is that all these 3 definitions in fact are equivalent. Once we have shown that, and so we're certain of this, then we will be able to use these 3 terms interchangeably, because vertices, extreme points, and basic feasible solutions will be exactly the same thing. Here is the statement of our theorem. Let P be a non-empty polyhedron, and let x star be a vector in P. Then the following 3 concepts are equivalent. X star is a vertex, X star is an extreme point, and X star is a basic feasible solution. Before diving into the proof of theorem 2.3, I want to give you a heads up regarding a theorem of linear algebra that I will be heavily using. I give you here the statement of the theorem. If you have already seen it, great. If not, I strongly recommend that you try to prove this theorem. Everything you need are basic facts from linear algebra, which are given in theorem 1.3 in the textbook. So let's get to the statement. Let AI transpose X equal to BI for I in an index set I be constraints in Rn. Then the following are equivalent. A. There exist n constraints among these which are linearly independent. B. The span of the vectors AI for I in I is all of Rn. From the definition of span, this means that every element of Rn can be written as a linear combination of the vectors AI. Finally, C. The system of equations AIX equal to BI for all I in I has a unique solution. Now that we have refreshed our linear algebra memory, let's get to the proof of theorem 2.3. In theorem 2.3, we have to prove the equivalency between these 3 concepts: vertex, extreme point, and feasible solution. So what we're going to do is divide the proof in three parts. In the first, we're going to prove that A implies B. Then we're going to show that B implies C. And finally, that C implies A. This will give us a complete proof of the theorem. Before starting to show these three implications, let me settle some notation regarding how our polyhedron P is given to us. So without loss of generality, P is represented in terms of constraints of only two forms, AI transpose X greater than or equal to BI, and equality constraints AI transpose X equal to BI. This is because if we have any constraint that is a linear inequality in the other direction, so AI transpose X less than or equal to BI, we can always multiply it by -1 and obtain an inequality constraint of the form greater than or equal to. So let's then get to the first part of the proof. So in the first part, we're going to show that A implies B. So we suppose that A hold, so that X star in P is a vertex. Directly from the definition, this means that there exists a cost vector C such that C transpose X star is strictly smaller than C transpose Y for every Y in P different from X star, with Y different from X star. Instead, in the definition of extreme point, we have two vectors y and z and a scalar lambda. So let's pick them. Let y in P, z in P, with a y different from x star and x star different from z, and 0 less than or equal to lambda less than or equal to 1. Since x star is a vertex, we immediately know that the cost of x star is strictly smaller than the cost of y, and the cost of x star is also strictly smaller than the cost of z. Now we're going to show that no point of the form lambda y plus 1 minus lambda z can ever be x star, which then implies that x star is an extreme point. How can we do that? Well, the idea is to look at the cost of all the vectors in the segment between y and z. So this is C transpose times lambda y plus 1 minus lambda z. We can just expand and obtain lambda C transpose y plus 1 minus lambda C transpose z. We have just seen that C transpose y and C transpose z are strictly larger than C transpose x star. So let's replace. So what we have written is strictly larger than lambda C transpose x star plus 1 minus lambda C transpose x star. But this quantity that we have just written is exactly C transpose x star. So what did we understand from these calculations? We've understood that the cost of a vector of the form lambda y plus 1 minus lambda z is always strictly larger than the cost of x star. Therefore, x star is different from lambda y plus 1 minus lambda z, and x star is an extreme point. This concludes the proof of A implies B. The next implication that we're going to prove is that B implies C. Next, we're going to show that B implies C. Equivalently, we show that not C implies not B. This means that we are assuming that x star is not a basic feasible solution, and we show that x star is not an extreme point. To show that the vector x star is not an extreme point, what we will be doing is construct explicitly vectors y and z such that x star is the midpoint of y and z, and both y and z are in P. Of course, we're going to be using the fact that x star is not a basic feasible solution. The definition of basic feasible solution concerns active constraints. Therefore, let's look at all the active constraints at x star. Let I denote the index set of the active constraints. So the set of I such that AI transpose x star equal to Bi. Since x star is not a basic feasible solution, there are no n linearly independent vectors among the AI for I in capital I. Now we use our theorem 2.2 of linear algebra. By theorem 2.2, and specifically we're using not A implies not B. We obtain that the vectors AI for I in capital I lie in a proper subspace of Rn. So there exists a non-zero vector, let's call it D, in Rn, orthogonal to the subspace. If it's not clear to you the existence of such a vector D, this is a great exercise to refresh your memory of linear algebra. Then AI transpose D equal to 0 for every I in I from the orthogonality. Now it's time to construct the vectors y and z as promised. Let's see an example. Let's say we're looking at a polyhedron like this one, and here's our x star. In this case, the only active constraint is the one corresponding to the segment where x star lives, and the corresponding vector AI will be orthogonal to this segment. Therefore, in this case, the vector D goes exactly along the segment. As you can see, this vector D is extremely useful for us because we can construct a new vector Y by going from x star in the direction D, and similarly we can construct a vector Z by going from x star in the direction minus D. And if we're careful to not go too far, then both Y and Z will be still in the polyhedron, and the segment joining Y and Z will contain x star, showing that x star is not an extreme point. So let's do this. Let epsilon be a positive number. You should think about this epsilon as a very small number, and define y as x star plus epsilon d, and z is equal to x star minus epsilon d. Next, we need to check that for epsilon small enough, then both y and z are still in P. We're going to look separately at the constraint indexed by the index set capital I, and then we're going to look at the other ones. So for I in capital I, we have AI transpose Y. This is equal to AI transpose X star plus epsilon AI transpose D, where we just replaced Y with its definition. And then due to the orthogonality between AI and D, this is equal to AI transpose X star, which is equal to B from the definition of capital I. Then for I not in I, we have AI transpose Y equal to, once again, we just need to substitute AI transpose X star plus epsilon AI transpose D. And this is then strictly larger than BI. Why is this the case? Because we know that AI transposed X star is strictly larger than BI, and so we can always make epsilon small enough so that epsilon AI transpose D added to AI transpose X star is still strictly larger than BI. So let me write where the last inequality holds for epsilon small enough because AI transpose X star is strictly larger than BI. I leave it as an exercise for you to figure out exactly for which values of epsilon this is true. Therefore, we have shown that Y is in P, and symmetrically you can show that Z is in P. And at this point we're done because X star is simply the midpoint of Y and Z, and so it can't be an extreme point. This concludes the proof that B implies C, so in order to show our theorem, we only have to show that C implies A. This means that we are assuming that X star is a basic feasible solution and we want to show that it's a vertex. Once again, the definition of basic feasible solution is in terms of active constraints, while the definition of vertex is in terms of being a unique optimal solution to some linear programming problem. Therefore, what we have to do here is essentially use the information on the active constraints on X star to obtain an objective function whose unique optimal solution is X star. Let's see immediately the very simple idea of this proof in an example. So let's say that this is your polyhedron and this is your X star. And as you can see, the two active constraints are those corresponding to these two segments. The corresponding orthogonal vectors are this one for the inequality on the left and this one for the inequality on the right. Now what's the idea? The idea is to just sum these two. In this case you will obtain this new vector, let's call it C, and as you can see from the picture, x star is the unique minimum of the linear programming problem with objective function Cx and feasible region P. In our proof, we will show that this doesn't happen only in this example, but it always happens. So let x star be a basic feasible solution and let I be the index set of the active constraints at x star. Let's define immediately our C vector. So it's the sum of all the AI for all I in I. Let's first look at the objective value of x star. We have C transpose x star equal to the sum for I in I of AI transpose x star, which is exactly the sum of BI for I in I from the definition of capital I. On the other hand, let's look at the cost of any other vector x in P. For every x in P and for every I, we have AI transpose x greater than or equal to BI from feasibility. Therefore, we obtain that C transpose x is the sum for I in I of AI transpose x by definition of C, and this is then greater than or equal to the sum for I in I of BI. So the objective value of x star is a sum of BI for I in I, and any feasible point has objective value greater than or equal to that. This immediately tells us that x star is an optimal solution to the problem. This of course is not enough to conclude that x star is a vertex, because we have to show that x star is the unique optimal solution. So let's understand when in the latter inequality, let's denote it by star, we have equality, because this will tell us exactly which are the vectors x in P that are optimal. Well, equality holds in star if and only if all the inequalities that we have used to derive star are actually equalities. So if and only if AI transpose x equal to BI for all I in I. What we want to do is show that only x star can satisfy this condition. And to do so, we will finally use the remaining part of the definition of basic feasible solution, that there are n linearly independent constraints that are active at x star. We can now use again our linear algebra theorem, so theorem 2.2, and obtain that x star is the unique solution to the system of equations aix equal to bi for I in I from theorem 2.2, and I'm using the implication A implies C in that theorem. X star is the unique solution to the system of equations aix equal to bi for I in I. Therefore, x star is the unique minimizer of the objective function C transpose X over P, and so X star is a vertex of P. And this concludes our proof of C implies A, and it concludes the proof of the full theorem. Let's now get back to the slides. We have now shown theorem 2.3, so we're now fully convinced that vertices, extreme points, and basic feasible solutions are indeed the same thing. And from now on, we're gonna use the terms interchangeably. In particular, this allows us to make an interesting observation about these three definitions. In fact, we have seen that the definitions of vertices and extreme points were geometric, meaning that they didn't depend on the representation of a polyhedron, but only on the polyhedron itself. On the other hand, the definition of basic feasible solution seems to depend on the specific representation used, because in such a definition we explicitly use the system of inequalities defining P. However, the fact that basic feasible solutions are vertices immediately tells us that also the definition of basic feasible solution is independent of the representation given, even if this is not immediately apparent from the definition. A question that I have for you is whether the property of being a basic solution depends on the representation of the polyhedron given or not. Directly from the definition of basic solutions and basic feasible solutions, we obtain that for a given polyhedron, the number of basic solutions or of basic feasible solutions is always finite. How can we see that? So let's look at a polyhedron which is always given by a finite number of linear inequalities. Let's say these are m linear inequality constraints, and let's assume, as always, that our space is Rn. Now, in any basic solution, we have n linearly independent active constraints that define such a point. And this immediately implies that the number of basic solutions is upper bounded by the number of ways that we can choose n constraints out of m, which of course is a finite number. This corollary gives us immediately an interesting idea. We have discussed how in the most interesting cases of linear programming problems, there's always an optimal solution that is a basic feasible solution. We have not yet shown that, but I already told you that this is the case. And this corollary, therefore, gives us immediately an interesting idea on how to solve a linear programming problem. We could just enumerate all the basic feasible solutions, for each one of them calculate its objective value, and select the one with the best objective value. This will be an optimal solution of our linear programming problem. This is true. This algorithm works and it's correct. This algorithm also runs in finite time because of the corollary we have just seen. Unfortunately, even though the number of basic feasible solutions is finite, it can be very large. And it's not even difficult to come up with examples. Consider the cube in Rn given by xi between 0 and 1 for every index I. The basic feasible solutions of the unit cube are all the binary vectors in Rn. So all the vectors with n components and with each component being 0 or 1. And in total these are 2 to the n basic feasible solutions. We have not yet discussed the computational complexity, but such a number is very large, essentially because it has the n in the exponent. It turns out that to obtain more efficient algorithms for linear programming, we will need some more interesting ideas. One idea that will be at the heart of the simplex method that we will be studying in detail in chapter 3 is that of jumping from a basic feasible solution to one that is close by. But what does it mean to be close by? Next, we will introduce the concept of adjacent basic solutions, which essentially allows us to formalize this concept of solutions that are close to each other. Let's first see in an example what we want to define. For example, let's consider the basic feasible solution C. I want to define an adjacent basic feasible solution to be D and F, because these are the closest to it. Similarly, the adjacent basic feasible solutions to D should be C and E. We can immediately formalize this concept by giving a definition, and we can even define adjacency for basic solutions instead of for only basic feasible solutions. So let's see the definition. Two basic solutions to a set of linear constraints in Rn are said to be adjacent if we can find n-1 linearly independent constraints that are active at both of them. In our example, n is 2, so this number becomes 1. And in fact, the vector D is adjacent to E because they lie on the same active constraints given by this line. And similarly, D and C are adjacent because they lie on the same line, this one, which corresponds to a constraint. Once again, this definition holds for all basic solutions and not just for basic feasible solutions. So for example, also A and D are adjacent, and also A and C are adjacent. Interestingly, if two adjacent basic solutions are also feasible, then all the line segment that joins them is contained in the polyhedron, and it's called an edge of the feasible set. In particular, in our example, the edges of the feasible set are the segment CD, the segment DE, the segment EF, and the segment FC. Here we have a higher dimensional example. It's a three-dimensional polyhedron. I have highlighted here in red two basic feasible solutions, and they are adjacent. In fact, in this case, there are 3 minus 1 equal to 2 linearly independent constraints that are active at both of them. One of these constraints is the one that corresponds to this green pentagon in the front, and the other constraint is the one that corresponds to this other green pentagon here on the side. It's clear from the picture that both basic feasible solutions satisfy those two constraints at equality, and that these two constraints are linearly independent because the two corresponding planes are not parallel. This concludes our video on vertices, extreme points, and basic feasible solution. Note that all these concepts have been defined for any polyhedron. In the next video, we will get back to polyhedra in a standard form representation, and in particular, we will see how these definitions can be specialized for such polyhedra.